right, we are going to finish up our lesson with questions number 9 and 10. In this section, before you got to this, it said, two equations you wrote in items 3 and 6 form a system of linear equations. To determine the solution of a system of linear equations, you must identify all the coordinate ordered pairs that make both equations true. One method is to graph each equation and determine the intersection point. And you have this math terms, which says two or more linear equations with the same variables form a system of linear equations. Number 9, graph each system of linear equations, give each solution as an ordered pair. Check that the point of intersection is a solution of both equations by substituting the solution values into the equations. So we're going to graph the 2x minus 10. So I'm going to start at negative 10. We go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and so forth until we connect our dots with a line. It's important that we make sure that this line is as straight as possible to make sure that our intersection matches. Okay, now we're going to start at positive 5. This one says go down 3 over 1, down 3 over 1, down 3 over 1, down 3 over 1, so forth, like so. Connect these dots with a line. Okay, question is, what's the intersection point? Right here, which looks to be 3, negative 4. Now, the next part of the equation, or the next part of the problem, says to check your answer into both of these equations to make sure it works. So we would do negative 4 equals 2 times 3 minus 10. Oops, didn't mean to put that parentheses there. That's a screw up. Sorry. So we've got 6 minus 10, which is indeed negative 4. So that works out because those equal each other. Let's plug it into the next one. Negative 4 equals negative 3 times 3 plus 5. Well, negative 3 times a positive 3 is negative 9. And negative 9 plus 5 is indeed negative 4. So those are indeed equal, which makes this solution the point where the two lines meet and the solution to our problem. B, reason abstractly. Edgar has 9 coins in his pocket. All of the coins are nickels or dimes and are worth a total of 55 cents. The system shown below represents this situation. How many of each type of coin does Edgar have in his pocket? Let N represent your nickels. Let D represent your dimes. So we want to solve these equations. And I'm actually going to solve them for D. Okay. So we're going to solve these for D. So this would be D equals 9 minus N. So I'm going to start at positive 9. And we're going to go down 1 over 1, down 1 over 1, down 1 over 1. Again, you want to make sure it's as straight as possible to make sure that your intersection point lines up. All right, this one's going to be 2D equals 11 minus N. So then we have to do D equals 5.5 minus 1/2 N. So we're going to start at 5.5, which was halfway here. And you're going down 1 over 2 each time. Down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. Intersection right here at 7, 2. Which means what? We have 7 nickels, 2 dimes. Let's double check this. 7 plus 2 equals 9. Well, that's right. We've got 7 plus 2 times 2 equals 11. Well, 7 plus 4 does indeed equal 11. So that checks out for both of those. So 7 nickels and 2 dimes in his pocket. Let's flip over to the next page. All right. Number 3 asks us to graph these two equations. So we're going to start at -5. And here it goes, up 3 over 1. Up 3 over 1. Up 3 over 1. Up 3 over 1. Here. Down 3, back 1. Looks like this line right here. Yeah, that's right. Okay. Like so. Okay. Now let's start at +4. This time we go down 2 over 1. Down 2 over 1. Down 2 over 1. Like so. Ooh. Okay, my problem is this does not cross at a crosshair. So we would want to graph this in our calculators to find the intersection point. And whenever I return on Wednesday, I will show you how to do that. But bear with me, the answer to this would be 9/5, 2/5. 9/5, 2/5. So we would do 2/5 equals 3 times 9/5 minus 5. Well, this would be 27/5. And we would convert this to a denominator of 5, so that would be 25/5. And 27 minus 5, 25 is indeed 2/5. So this one works out. Let's check it out in the other one. We would have 2/5 equals -2 times 9/5 plus 4. That's going to be -18/5. We want to convert it to have that denominator of 5. So we would make this 20/4. -18 plus 20 is 2/5. So this equals each other. So it works for both solutions. Again, this one I didn't draw very well, and I really should have graphed this on a graphing calculator. So I'll teach you how to do that on Wednesday when I return. Let's take a look at this particular problem. This would be y equals -3x plus 1. So I'm going to start at +1. We're going to go down 3 over 1. Down 3 over 1. Down 3 over 1. All right. Let's take a look at this one. All right, we would have 2y equals -6x plus 10. Then that would go to y equals -3x plus 5. So we're going to start at 5 here and go down 3 over 1, 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 like so. And making sure I draw this straight. What do we notice here? No intersection. E. What made finding the solutions to parts C and D challenging? Well, C, there was decimal answers, while with D, we had no intersection. So no point where the lines crossed. Lena graphs the system x minus 2y equals 3 and 2x minus y equals -3 and determines that the solution to be 1, -1. She checks her solutions algebraically and decides that the solution is correct. Explain her error. Okay, well, let's just check it. 1 minus 2 times -1 equals 3. Well, that's going to be 1 plus 2, and 3 does equal 3. Checks out for the first equation. Let's try it out for the second equation. 2 times 1 minus -1 equals a -3. 2 times 1 is 2. Plus 1, because the double negative there. 3 does not equal -3. She is incorrect. The solution must work must be true for both equations. It can't work for just one. It has to work for both. On to the wrap up of this lesson.